Hello everyone. Thank you for sharing for the first tutorial. In the second tutorial, I want to talk about the real-world applications and benchmarks. Uh, Given my background, I will talk about a little bit about LLM agents, IO training, and then uh, talk about the benchmarks. Basically, I want to do this tutorial because benchmarks somehow categorize how these planning are being used in modern research. Okay, I'd like to start with framing why many people refer 2025 as a year of agents. What change is not just bigger than language model, but a combination of three factors. We now have stronger reasoning models, largely driven by post-training and our reinforced learning training. These models can think longer horizons and maintain coherence across multiple steps. Sorry. Okay. Second, tool use and memory become much more reliable. Models are no longer just calling tools. Occasionally, they can decide when to use them, remember intermediate steps and result, and build on the past actions. And third, we finally saw the deployment-ready agent frameworks in the past year. I think there are a lot of large-scale agent frameworks for deployment and enterprise use, which made it practical to connect the models to real-world systems. Okay. As a result, planning unlocks something fundamentally new. LM moved from providing assistance like answering questions or suggesting next steps. They now perform end-to-end automation, where they plan and execute multi-steps workflows and coordinate across systems. In the rest of the tutorial, I'll focus on this real-world application enabled by this transition, and then the mainstream benchmarks we use to evaluate the planning and reasoning capabilities. Okay, first, once planning and reasoning become reliable, 2025 saw a surge of genuine new real-world applications. There are no longer just better chatbots, but systems they can plan, act, and adapt. We now have two personal assistants like Manus and Gemini AI systems. They can organize information and support multi-step knowledge work, help us to do a lot of daily work. In software development, code agents like Cursor and Cloud Code are super powerful. They can plan and change across the code base and execute non-trivial workflows. In robotics and embodied AI, such as Tesla Optimus and Helix increasingly use language model as a high-level planner over perception and action. In the enterprise system like Microsoft Copilot and Salesforce Einstein Copilot coordinate complex business workflows, while research agents like OpenAI Deep Research and Perplexity research mode can plan multiple steps, investigation, and synthesize a lot of evidences. Across all these domains, the common thread is that planning and reasoning, which they form the backbone of modern LLM agent. So this slide explains why planning and reasoning are so central to modern large language models and large language model agents. On the left, reasoning is about inference. Given some information, the model performs a sequence of inference steps to arrive at the final conclusion. This is what supports multi-step problem solving and consistency beyond surface level QA. On the right, planning goes a step further. Starting from the goal, the model must choose a sequence of actions, anticipate the state change, and reason about whether these actions will actually lead to the goal. These abilities are foundation to the large language model-based agents. Without reasoning and planning, LLM cannot act autonomously or coordinate multi-step workflows. These abilities are much harder to fake than standard QA questions because success requires maintaining coherent intermediate steps and handling state changes, not just providing a final textual answer. Okay, so far I have discussed what planning and reasoning capable LM agents can do in the real world. The natural next question, why is the, 2025 witnessed this change, and what enables these capabilities? The key breakthrough was reinforced learning for LM reasoning. Instead of relying on scalable or supervised fine-tuning alone, in the last year, ARIA-based post-training allowed models to acquire reasoning-like behaviors through feedback and optimization over longer horizons. A central idea here is the verifiable reward signals, which we call it reinforced learning with verifiable rewards. With RLVR, correctness can be checked autonomously using unit tests and simulators, rather than relying on human feedback. This provides a much more efficient and scalable training signal for complex problem solving. A concrete example is DeepSeek R1, which is published early last year. It applied ILVR with GRPO and reached reasoning performance comparable to top proprietary models, demonstrating that IL can effectively teach a model to reason, and it's quite simple. So in the last year, a lot of people are following this approach and training LLMs with much stronger reasoning capabilities. This slide shows why 2025 is often called the year of reasoning LLMs. The key point is that after the success of model like DeepSeek R1, AI-based reasoning training was rapidly adopted across the field. Now every AI lab have their thinking version of models, and reasoning focused LLM moved from being a novelty become the mainstream of models. This figure illustrated what changed recently. With the standard scaling, performance on difficult reasoning tasks improved only modestly over time. But once the AI-based training was applied, we saw a sharp jump in performance in 2025. This translated into real benchmark gains. On challenging planning benchmarks such as natural plan, task early models that almost they can never solve, under 5% success rate, are now being solved at more than 50% success rate. This kind of leap explains why planning and reasoning suddenly became viable foundations for real-world LLM agent. Okay, this is after the background. This is outline of my overview on the benchmarks. I organized tutorials around four benchmarks, four category of benchmarks, because the benchmarks, I think benchmarks provide concrete lens for understanding how LLM-based planning methods are actually used in practice, which has some overlap with Shirin's talk. They roughly reflect the real application settings, encode the assumptions we made about planning capabilities, and importantly, offer feedback that can guide the design for better planning approaches. I will start with natural language plan generation, where large language model produce explicit multi-state plan directly from text, such as travel itinerary or task schedules. Then I will move to reasoning about actions and change, focusing on whether models can track state, understand the action effects, and evaluate plans. Next, I will cover natural language to PDDL translation, which connects LLM with classical planning by mapping the text descriptions into formal planning representations. And finally, I will discuss interactive agents and environments where the LLM act in simulated worlds, including embodied tasks and web and GUI tasks. Okay, the first category of benchmarks evaluate LLM's capability to generate natural language plans, which is one of the most direct way to evaluate LLM planning. Given an open-ended goal, such as planning a trip, the model must generate a complete, temporally ordered plan rather than a single answer. The challenge is not just about reasoning locally. The models should maintain coherence across multi-steps while handling constraints that are often implicit, like time, feasibility, or resources. As shown in this figure example, the plan quality is evaluated in human-centric way, whether the itinerary is realistic, useful, and makes common sense. This makes natural language plan generation especially important because they closely reflect how LMs are actually used in real-world applications. For this category of evaluation benchmarks, I list 4 representative works. This table compares these representative benchmarks and highlights how the fields are evolved over time. Early benchmarks like the Autoplan bench focus on broad coverage across domains with limited realism and personalization, and they primarily evaluate whether a plan is valid. Natural plan, in the middle, the natural plan and the travel planner move closer to real-world use cases, emphasizing everyday tasks or travel planning and focusing on strategy, quality, and feasibility. Finally, the trip tailor, which was released in the last year and the latest tape. It is narrowly scoped to travel, but with very high realism and a strong personalization, and it evaluates plan against the human level quality rather than just correctness. This progression reflects a broad shift from abstract plan validity towards realistic user-centered planning scenarios. So the benchmarks actually develop as we developing the AM planning. Okay, the second category of benchmarks focus on reasoning about actions and change, which test a different aspect of planning capabilities. If the model can reason about actions and state change, they actually have a strong reasoning and planning capabilities and can use in more diverse applications. Here, the plan is already given. The model's task is not to generate actions, but to mentally simulate them, checking whether each action is executable, tracking how the state changes, and determining whether the final goal is actually achieved. As the block word example shows, this requires precise state-centric reasoning, understanding the preconditions, action effects, and what they stay unchanged. Errors will accumulate quickly if the model loses track of the state. Because of these benchmarks closely align with classic planning concepts like fluence and plan validity, and they strongly stress system 2 level reasoning rather than surface level pattern matching. I also give 4 representative benchmarks to evaluate this kind of ability of the models. These benchmarks evaluate are for reasoning about actions and state change, showing how the complexity of evaluation has increased over time. Early benchmarks like track focus on step level state tracking is in simple domains such as block word. After that, the action reasoning bench explains this in richer domains and rule-based reasoning. ACP bench goes further by testing deeper structure and causal reasoning grounded in classical planning concepts. MapStore is the latest work, represent a qualitative shift. It moves beyond static, fully observable setting to a dynamic, embodied 3D environment with multiple agents and partial observability. So this trend is moving from static to dynamic, from single agent to multi-agent evaluation. Together, these benchmarks illustrate a progression from controlled symbolic reasoning to more realistic agent-centric reasoning about actions and change. The third category of application or benchmarks focus on natural language to PDDL planning transition. So after the transition, we can use classic planning tools and efficient search algorithms, which sit as the inference. So this kind of approach sits as the interface between the LM and the classic planning. Here, the goal is not to generate a plan directly, but to translate an informal language description into a formal PDDL problem statement that a classical planner can solve. As the figure shows, this requires grounding language into symbolic representations like objects, predicates, and goal conditions. What makes this challenging is that formal correctness really matters. During the transition, the large language model cannot have hallucinations and any kind of errors. Otherwise, the classic planner cannot execute. Even small mistake can cause the planner to fail entirely. Well, I mean, sometimes use natural language planning can accept some kind of error. Because of these evaluations, often the planner in the loop. If the planner succeeds, the transition is correct. These benchmarks are important because they directly bridge neural language models and symbolic planning systems, testing whether the LMs can serve as a reliable interface between the two. This table summarizes representative benchmarks for natural language to PDDL translation and show how the Fox has evolved. NL to PDDL and the planetarium concentrate on translation natural language into formal, correct PDDL problems, where success is measured by whether a classic planner can solve the output. This places a strong emphasis on formal rigor and precise symbolic grounding. LM plus P takes a slightly different approach by jointly evaluating plan generation and symbolic representation, focusing on more plan validity than strict planner success. Planet, released in 2025, step back and provide a comparative analysis across many such benchmarks, helping us to understand the strengths and limitations at a broader level. Together, these benchmarks evaluate whether large language models can reliably bridge natural language and symbolic planning systems. Okay, the final set of benchmarks focus on interactive agents in simulated environments where the planning and reasoning are embedded in closed-loop interaction. Here, the model is not just generating a plan at once, it must repeatedly plan, take actions, observe the environment change, and adapt based on the feedback. As shown in this example, this I think is from a kitchen environment. Each action has concrete effect, and the mistakes can propagate if the agent fails to recover. Okay. Sorry. My mouse is not working. Oh, okay. Here, the model is not just to generate the plan at once. It must repeatedly to plan and take actions step by step, observe the environment, and adapt based on the feedback. These tasks are challenging because the agent operates under partial observability and uncertainty without full state access. As a result, evaluation goes beyond simple task completion and emphasis on robustness, recovery, and safety. These settings closely reflect how real-world LLM agents behave and when interacting with environments rather than static text. So, okay. So in the interaction environments, I categorize into two type groups. First one is embodied tasks, and second one is the web and GUI agents. This table highlights their difference. From a planning perspective, in embodied settings, the agent operates through navigation and manipulation, relying on perceptions such as vision and state, and dealing with physical constraints like occlusion, timing, and physics. In planning challenges here often involve coordination and recovery, especially when actions have irreversible effects. In contrast, web and GUI environments are less physical but cognitively demanding. Actions are clicks and text imports. Perceptions come from HTML and UI elements. And the main challenge lies in long horizon workflows, memory and tool use, and generalization to unseen websites. Although the interface differ, but both settings stress the planning under uncertainty, just in different forms. So on this table, I listed both benchmarks for embodied tasks and web and GUI tasks. On the embodied task side, Alpha-8 and AlphaWord focus on grounding language into action sequences in household settings with or without version. Textcraft and robot only push toward longer horizons, introducing strategy, parallel actions, and timing constraints. Safe Agent Bench is an explicit safety dimension, testing whether the agents can plan conservatively under hazardous conditions. On the web and GUI agent task side, Web Arena evaluates end-to-end workflows in simulated websites, while Mind2Web significantly raised the bar by requiring generalization to real, unseen websites. Agent Bench provides a broader comparative view across tasks and tools, helping position agents' capability along multiple dimensions. So together, these benchmarks illustrate a clear progression from controlled environments to realistic, noisy, and long horizon settings, where the agent can interact with the environment infinitely, which is essentially for evaluating the planning-centric agents. Okay, finally, let me conclude with 4 key takeaways from this tutorial. First, planning and reasoning are what turn the large language model into real-world systems. Without these abilities, LM remain question-answering engines. With them, we get the goal-directed agents that can coordinate workflows, interact with software, and operate in complex environments. Second, reinforced learning has been the real game changer. AI-based post-training in 2035 dramatically improved the long horizon reasoning and planning capabilities of LM. Models can now generate plans, revise them, and follow through, capabilities that were simply not reliable before. Third, benchmarks are now do more than evaluate performance. They're growing the ecosystem of planning and reasoning. Benchmarks actively drive progress by revealing where models fail, guiding training, and bridging the classical AI planning and modern LLM, large language models. Finally, we are seeing a broader paradigm shift. Planning-capable LLM sit at the intersection of neural and symbolic approaches, combining flexibility of structure. While we are not fully reliable planners yet, we are clearly moving closer. So with that, I hope this tutorial helped clarify where real-world applications are emerging and why careful evaluation is essentially and valuable. Okay, thank you. Any questions?
start with a question.
Okay.
So on the benchmarks, what do you think should happen to avoid potential data contamination of any of the benchmarks that are available on the web?
So this is a quite real problem in nowadays training. So I saw a kind of approaches to not publish the explicit problem statement online, but to translate into some encrypted words online, so such as this data will not leak to the pre-training and post-training stage. But for evaluating the real performance, you need to convert this encrypted data into plain text locally on your server or computer, such that we can ensure a fair evaluation and performance. And that's normally what people do. And I saw a lot of benchmarks are doing this, not in planning, but also a lot of QA tasks are also in this way. Okay, if no question, we can proceed to the coffee break. And after the coffee break, we will have Professor David Xu from National University of Singapore. He's a renowned researcher in robotics, and he will talk about how planning in robotics nowadays.